We think we understand the moon. We've walked on it. But if it vanished, Earth wouldn't slowly adapt. It would destabilize. The oceans would behave differently. The climate would stop being predictable. The planet's tilt would begin to wander. Life didn't just evolve with the moon. It evolved because of it. This is why our moon is more important than we think. The moon orbits Earth at an average distance of 384,400 kilometers. That's about 30 times the width of our planet, close enough to dominate our night sky, far enough to seem distant and unreachable. But distance is not the important part here. What matters is mass. The moon weighs 7.35 times 10 to the power 22 kilograms. That's roughly 1% of Earth's mass. And while that might sound insignificant, it's enormous compared to other moons in the solar system. Consider this. Jupiter's largest moon, Ganymede, is bigger than Mercury, but compared to Jupiter, it's practically invisible. Ganymede represents 0.00008% of Jupiter's mass. The moon represents 1.2% of Earth's mass. That makes Earth and the moon something unusual. Not quite a double planet system, because the barycenter, the point around which both bodies orbit, is still inside Earth, but close. And that mass ratio changes everything, because when two bodies orbit each other, they don't just move through space, they pull on each other. They create forces that ripple through rock and water and air. We call these forces tides. Tides are the most visible effect of the moon's gravity. Everyone knows that the moon causes the ocean to rise and fall twice a day, but not everyone understands why. Here's how it works. The moon's gravity pulls on Earth, but it doesn't pull evenly. The side of Earth facing the moon feels a stronger pull than the side facing away. This difference in gravitational force is called a tidal force. Water is liquid. It flows. So when the moon pulls on Earth, the ocean closest to it bulges outward. At the same time, the water on the far side of Earth also bulges outward because it's being pulled less than the solid Earth beneath it. Two bulges, two high tides. As Earth rotates beneath these bulges, any given point on the surface passes through both high tides and both low tides every day. That's why coastal cities experience two high tides, roughly 12 hours apart. But the moon is not the only force at work here. The sun also exerts tidal forces on Earth. Solar tides are weaker than lunar tides, about 46% as strong, but they still matter. When the sun, moon, and Earth align during a new moon or full moon, their tidal forces combine. These are called spring tides. High tides are higher, low tides are lower. When the sun and moon are at right angles to each other during a first or third quarter moon, their forces partially cancel out. These are called neap tides. High tides are lower, low tides are higher. This rhythm has been going on for billions of years, and it has shaped life on Earth in ways we are only beginning to understand. The intertidal zone is a narrow band between the highest and lowest tides. It is one of the harshest environments on Earth. Organisms living there must survive both underwater and exposed to air. They endure temperature extremes. They face desiccation. They are battered by waves. But life thrives there. All of these species have evolved to synchronize their behavior with the tides. Some lay their eggs during specific tidal cycles. The California grunion, a small fish, times its spawning to coincide with the highest spring tides. The eggs are buried in the sand and hatch 2 weeks later when the next set of high tides washes them out to sea. Without the moon, this system would collapse, because without the moon, tides would be much weaker. The sun alone would still create tides, but they would be only about 1/3 as strong as the tides we experience today. Weaker tides mean a narrower intertidal zone, less habitat, more competition, fewer species able to survive. And it's not just the intertidal zone. Coral reefs rely on tidal cycles to regulate water temperature and nutrient flow. Many species of crabs, worms, and fish use moonlight as a trigger for reproduction. The lunar cycle governs breeding seasons for species across the planet. Remove the moon, and these rhythms disappear. The ocean would still move, but it would move differently, and life would have to adapt or die. The moon does more than pull on the oceans. It pulls on Earth itself. The solid crust of the planet experiences tides just like the ocean. These are called Earth tides, and they cause the ground to rise and fall by as much as 30 centimeters twice a day. We don't notice this because the entire landscape moves together, but the effect is real. It has been measured, and it has consequences. One of those consequences is that the moon is slowing Earth's rotation. Here's how it works. As Earth rotates, the tidal bulges created by the moon's gravity don't stay perfectly aligned with the moon. Earth's rotation drags the bulges slightly ahead. The moon's gravity pulls back on these bulges, creating a torque that opposes Earth's rotation. This torque is weak, but it is constant, and over time, it has a profound effect. 4.5 billion years ago, when Earth was young, a day lasted only 3 to 6 hours. The moon was much closer then, orbiting at about half its current distance. Tidal forces were far stronger. Since then, Earth's rotation has been slowing down. Days have been getting longer. Today, a day lasts 24 hours, but it's still slowing. Every century, the length of a day increases by about 1.7 milliseconds. That might not sound like much, but over millions of years, it adds up. And there's more. The energy being drained from Earth's rotation doesn't just disappear, it's transferred to the moon. That energy pushes the moon into a higher orbit. Laser ranging experiments using mirrors left on the lunar surface by Apollo astronauts have confirmed this. The moon is moving away from Earth at a rate of 3.8 centimeters per year. That's about the speed at which human fingernails grow. It's slow, but it's measurable. And it's been happening for billions of years. Now we need to talk about Earth's axis. Right now, Earth is tilted at 23.4 degrees relative to its orbital plane around the Sun. This tilt is the reason we have seasons. When the northern hemisphere is tilted toward the Sun, it experiences summer. When it's tilted away, it experiences winter. But that tilt is not fixed. Earth wobbles as it spins. Like a spinning top that's been nudged from the side, Earth's axis traces out a slow circle in space. This motion is called precession, and it takes about 26,000 years to complete one full cycle. Right now, Earth's north pole points toward Polaris, the North Star. But 13,000 years ago, it pointed toward Vega, and 13,000 years from now, it will point toward Vega again. This is normal. All rotating planets experience precession, but here's the critical part. The amount of wobble, the variation in Earth's axial tilt, is small. Over the past million years, Earth's tilt has varied between 22.1 degrees and 24.5 degrees, a range of only 2.4 degrees. That stability is not typical. Mars, for example, has no large moon. Its axial tilt varies wildly, swinging between 0 degrees and 60 degrees over millions of years. When Mars is tilted at 0 degrees, it has no seasons. When it's tilted at 60 degrees, the poles receive more sunlight than the equator. The climate swings are extreme. Earth does not experience these swings, and the reason is the moon. The moon's gravity acts like a gyroscopic stabilizer. It exerts a constant torque on Earth's equatorial bulge, damping out variations in axial tilt. Without the moon, computer simulations suggest that Earth's axial tilt would vary by as much as 10 degrees or possibly more over hundreds of thousands of years. 10 degrees might not sound like much, but it's enough to cause massive climate shifts. Let's talk about ice ages. For the past 2.5 million years, Earth has been cycling between glacial and interglacial periods. During glacial periods, ice sheets cover much of North America and Europe. During interglacial periods like the one we're in now, the ice retreats. These cycles are driven by variations in Earth's orbit and axial tilt. This is known as the Milankovitch cycles, named after the Serbian scientist Milutin Milankovic. There are three main cycles. First, the shape of Earth's orbit changes over time. Sometimes it's more circular, sometimes it's more elliptical. This affects how much sunlight Earth receives at different points in its orbit. Second, Earth's axial tilt varies between 22.1 and 24.5 degrees over a 41,000-year cycle. A higher tilt means more extreme seasons. A lower tilt means milder seasons. Third, the direction Earth's axis points changes over time due to precession. This affects which hemisphere receives more sunlight during summer. Right now, Earth's tilt is 23.4 degrees and decreasing. We are in an interglacial period. The ice sheets that once covered Canada and Siberia have melted, but here's the critical point. Even a 1-degree change in Earth's axial tilt can trigger an ice age. When the tilt decreases, summers become cooler. Less ice melts. Snow accumulates year after year. Over thousands of years, that snow compresses into glaciers. The glaciers spread. Eventually, they cover continents. That's what a 1-degree variation does. Now imagine what a 10-degree variation would do. Without the moon, Earth's climate would be far less stable. Ice ages would be more frequent and more severe. The climate could swing from extreme heat to extreme cold on timescales of tens of thousands of years. Life would have to adapt constantly. Evolution would be forced to move faster. Complex ecosystems might never develop. The moon doesn't prevent ice ages, but it makes them predictable. It constrains the variation. It gives life time to adapt. Let's compare Earth to other planets. Mercury has no moon. Its axial tilt is only 0.03 degrees. There are no seasons, no climate variation, just a scorched surface facing the sun and a frozen surface facing away. Venus also has no moon. Its axial tilt is 177 degrees, meaning it rotates upside down and backwards. It's unclear whether Venus ever had a moon, but if it did, scientists believe it may have been destroyed by a second giant impact early in the planet's history. Mars has 2 tiny moons, Phobos and Deimos. They are too small to stabilize Mars's axial tilt. As a result, Mars's tilt varies between 0 and 60 degrees over millions of years. The climate swings are enormous. When Mars is tilted at high angles, the poles become warmer than the equator. Water ice sublimates into the atmosphere. The atmosphere thickens. Conditions change rapidly. When Mars is tilted at low angles, the poles freeze solid. The atmosphere collapses. The planet becomes a frozen desert. This is Mars today. A planet that once had rivers and lakes, now a barren wasteland. Part of the reason is the lack of a large stabilizing moon. Earth is different. Earth has a moon that is large enough to matter, large enough to stabilize the axial tilt, large enough to create predictable tidal forces and climate patterns. And that makes Earth unique. So where did the moon come from? The prevailing theory is called the giant impact hypothesis. About 4.5 billion years ago, a Mars-sized body collided with the young Earth. The impact was so violent that it vaporized a large portion of both objects. Debris was ejected into orbit around Earth. Some of that debris fell back, some escaped into space, but a significant amount stayed in orbit, eventually coalescing to form the moon. This explains several key features of the Earth-Moon system. First, the moon's composition is similar to Earth's mantle but lacks a large iron core. This makes sense if the moon formed from material blasted off Earth's outer layers. Second, the moon is depleted in volatile elements like water. This is consistent with the high temperatures created by the impact, which would have vaporized lighter materials. Third, the Earth-Moon system has unusually high angular momentum. A giant impact would transfer rotational energy to both bodies, spinning Earth faster and flinging the moon into orbit. The giant impact hypothesis is not perfect. There are still unanswered questions about the exact composition of the impactor and how the debris disk evolved into the moon. But it's the best explanation we have, and it suggests something important. Large moons like ours may be rare. Most planets in our solar system have moons, but most of those moons are small. Jupiter has 79 known moons. Saturn has 82, but none of them are large relative to their parent planet. Ganymede, Jupiter's largest moon, is bigger than Mercury, but it represents only 0.00008% of Jupiter's mass. The only other system in the solar system with a moon-to-planet mass ratio comparable to Earth's is Pluto and Charon. Charon represents about 12% of Pluto's mass, but Pluto is a dwarf planet, not a full-sized world. Outside our solar system, we have detected thousands of exoplanets, but we have not confirmed a single exomoon. This is partly due to observational limits. Detecting moons around distant planets is extremely difficult, but it also suggests that large moons may not form easily. A 2007 study using NASA's Spitzer Space Telescope looked for evidence of moon-forming collisions around young stars. The researchers observed 400 stars, all about 30 million years old, the same age our Sun was when the moon formed. They found dust around only one star. That suggests that giant impacts capable of creating large moons occur in only 5 to 10% of planetary systems. If that's accurate, then Earth may be unusually lucky, not just because it has a large moon, but because that moon has created the conditions necessary for complex life to evolve. The moon is moving away from us, slowly but steadily. In 50 million years, the moon will be noticeably farther away. In 500 million years, it will appear smaller in the sky. Total solar eclipses will no longer be possible, but the real changes will take much longer. In about 1.5 billion years, the moon's stabilizing influence will begin to weaken. Earth's axial tilt will start to vary more dramatically. Climate patterns will become less predictable. In 5 billion years, the Sun will expand into a red giant. It will likely engulf both Earth and the moon, destroying them completely. But even if Earth somehow survives, the moon will continue drifting away. Eventually, the Earth-Moon system will reach a stable configuration where both bodies are tidally locked to each other. Earth will always show the same face to the moon, and the moon will always show the same face to Earth. But that will take tens of billions of years. For now, the moon is still close enough to matter, close enough to pull on the oceans, close enough to stabilize the axis, close enough to make life possible. We take the moon for granted. It's always been there. It will always be there. Or so we assume. But the moon is not just a feature of the night sky. It's a fundamental part of Earth's habitability. It regulates the tides, which shape coastal ecosystems and drive nutrient cycles in the ocean. It stabilizes Earth's axial tilt, which prevents catastrophic climate swings. It slows Earth's rotation, which lengthens our days and allows complex life to evolve in a stable environment. Without the moon, Earth would still exist, but it would be a very different planet. The seasons would be unpredictable. The tides would be weak. The climate would swing wildly. Life might still emerge, but it would face far greater challenges. And that raises a question. If large moons are rare, and if large moons are necessary for stable climates, then how common is life in the universe? We don't know yet, but the moon gives us a clue. It tells us that habitability is not just about being in the right place. It's about having the right conditions, the right mass, the right orbit, the right stabilizing force. Earth has all of that. And it's all because of a collision that happened 4.5 billion years ago. A collision that gave us a companion, a stabilizer, a machine that has been shaping the conditions for life ever since. We call it the moon. But maybe we should call it something more. The architect of our world. For now, the moon continues its slow drift outward. It rises in the east and sets in the west. It waxes and wanes. It pulls on the oceans and steadies the axis. Most of us don't think about it, but the scientists do. They track its distance with laser beams. They study its composition with rock samples. They model its influence on Earth's climate over billions of years. And with every measurement, they find the same conclusion. The moon is not optional, it is essential. Not just for the tides or the seasons, but for the entire delicate balance that makes Earth a living planet. We owe more to the moon than we realize. And maybe that's the most important thing to understand. That pale gray sphere in the sky is not just a light in the darkness. It's the reason we're here at all.